Welcome everyone to our next keynote presentation with Bojan Tunguz, which is data science on GPUs. Over the past decades, the use of GPUs has had an enormous impact on machine learning and deep learning in particular. However, the acceleration that GPUs provide can be extended to all aspects of the data science pipeline, like data acquisition, data retrieval, data munging, non-DL machine modeling, model deployments, etc. In turn, accelerating data science processes provides data science practitioners with greater ability to be efficient, creative, and productive. In this talk, we'll showcase some of the ways that GPU acceleration benefits everyday data science workflows. Bojan is a Kaggle Grandmaster and has been ranked in the top 20 competitors across the entire world. So congratulations on that, and so glad to have you with us, Bojan.
Thank you, Stefan, and thank you for having me on this presentation. I'm going to switch now to full presentation mode for my document. Can everyone see the opening page?
Yes, it's live.
All right. Thank you, Stefan, again. So my name is Bojan Tunguz, as Stefan mentioned. I'm a machine learning modeler at NVIDIA Rapids and KGMon teams. Rapids is what's going to be main point of my presentation today. And the KGMon is a special team that we have at NVIDIA of currently 9 Kaggle Grandmasters. And our main task is promoting Rapids and competing in Kaggle competitions. So I'm going to give you a very brief overview of my talk. You probably all know what data science is, so I'm not going to bother you too much. I'm just going to give you a very extremely brief overview, so I have some context for what I'm going to be presenting later on in my talk. Then I'm going to mention what GPUs are, what CPUs are, and how they're all affected by Moore's law. And then I'm going to mention what we've done with the GPUs in data science so far. That's been mostly in the domain of deep learning, but now there's expansion of use of GPUs for all the other data science tasks. Main focus of my talk will be on the Rapids framework, which is several different libraries that try to capture most of the data science workflow on GPUs. Two main components are cuDF, which is a library that resembles Pandas and is used for ETL and similar data munging operations. The other one is QML, which is similar to scikit-learn and is used for modeling and machine learning tasks. The other part of a Rapids library, there are other Rapids libraries like cuGraph, cuSpatial, cuSignal, and several others that help with other more niche parts of the data science workflow, but they're also very advanced and very useful for speeding up data science workflows. And then there are a few libraries that are built on top of the Rapids, like NVTabular, Blazing SQL, and Streams, which help with speeding up other aspects of data science workflow. And finally, I'll give a brief mention of one of my favorite machine learning tools, is SHAP values. That's very recently, like within last couple of weeks, been incorporated into the GPU workflow for machine learning and data science. So what is data science? Well, there's no really single definition of it, and it's very much a practitioner-driven field. So it really depends who you ask and what they're actually doing in the daily job that really defines what data science is. There are many overlaps with other parts of computer science and statistics and other scientific endeavors that kind of bear on a definition of data science. And that really depends on which particular background a person who is pursuing data science is coming from. But there's very wide spectrum of things that data scientists actually end up working on in the day-to-day life, depending on their own background, depending on the company they're working on, and what kind of tasks they have to do, and similar considerations. And so it includes analysis, structure of the data, designing algorithms, designing processes for data science workflows, programming, problem solving, and general kind of knowledge generation. So here's one pretty expansive snapshot of what workflow for data science could look like. You have data acquisition, getting data from the outside world. It could be either raw data from the natural world, or it could be just acquisition from some kind of business process. There's data storage and retrieval, which for the longest time was one of the main occupation of what data scientists were doing. This is mostly in terms of relational databases and other data science products. Then more recently, data scientists have been kind of engaging much more in a task of cleaning and munging the data, exploring the data, visualizing data, doing some light analysis or deeper analysis, depending on what kind of project they're working on. Once you have a pretty good understanding of your data, many data scientists would work on the machine learning modeling, which is my own specialty and something that is very close to my heart, but it's a relatively small part of the whole data science workflow. Within the machine learning modeling, or like in addition to it, there's exploration of the features for the data science workflow, new feature engineering, which is very important for achieving a state-of-the-art model performance and other machine learning performances. There's once modeling is done, we analyze the data and we make some predictions. We would like to interpret what our models are predicting. So there's that part of data science workflow where we're actually looking at the models and seeing what they're actually telling us about the data, telling us about the process that we're trying to model. Finally, in many circumstances, you have to deploy your models in the real world to actually make it useful. So there's a model deployment, which some data scientists do. And once the model is deployed, most often the data that you encounter in the real world is not going to be as nice and well-behaved as the data that you prepare for yourself. So you need to have a continuous model monitoring. So all these aspects of the data science pipeline are part of what most data scientists at some point have done in their careers. However, most practicing data scientists don't engage in all aspects of data science pipeline. It's very common that some of them would be focusing one part of the pipeline, some of the others. In my own personal experience, I'm mostly focused on machine learning modeling and creating best possible predictive model. There's also a lot of overlap with other technical fields like software engineering, data analytics, data engineering, database specializations, and similar kind of workflows. So, data scientists don't work in vacuum. They're usually part of a big team, and they need to collaborate, interact with other practitioners. Another thing that needs to be emphasized and re-emphasized a lot is that the data science is not just a linear sequential kind of practice. It really is a very iterative and very non-linear way of making things happen. It really depends on a lot on the kind of data set and kind of tasks that you're really be working on. But in most cases, this iteration is a very core part of the data science workflow. So being able to do this iteration and then perform your tasks often and very quickly is a very important part of what makes a successful data science project. So this iterative work loop looks something like this. Again, because it's nonlinear, it doesn't necessarily mean that any one of these parts it's really the starting point. You can start with that idea, create an experiment, look at some kind of results, and maybe come up with a new idea. Or someone hands you over the results, and then you try to figure out what's the best way to model this data, get some idea, build a model, iterate. So iterative part is, again, crucial for very good and a very advanced machine learning modeling and data science practice. So, I cannot emphasize this point strongly enough. So, because it is iterative, it helps to have a very quick turnaround for any part of this process. So far, most of the data science workflow, aside from the deep learning, has been done on a traditional CPU computers and CPU systems. The only exception, or the big one, is, of course, neural networks, which somehow have become the dominant form of what people think about artificial intelligence and data science and all these things. But there's still very much a niche part in a broader spectrum of what data scientists do in their daily practice. Another thing about neural networks is they're one of the first data science algorithms where GPUs became very important in accelerating the research. And the main reason we do have such a strong acceleration of deep learning and machine learning projects over the last 10 years or so is because the GPUs have enabled almost exponential, well, more than exponential growth in performance for some of these machine learning tasks. GPUs are massively parallel computational devices. You have thousands of cores on a single die that can really perform a lot of operations in parallel, unlike CPUs, which are much more sequential. Even many core CPUs are much more sequential and much more limited in the way that they operate than GPUs are. It turns out that neural networks are very natural place to start using a parallel computation because their very nature is very parallel. However, all the other tasks that we can put in a data science pipeline can also be parallelized, and they have been more and more, and we have been moving more and more in that direction over the years. So here's a very brief history of neural networks and deep learning on GPUs. Very famously in 2009, Andrew Ng and his collaborators at Stanford figured out that you can really speed up some of these neural network calculations if you put them on very parallel graphical processing units, which were, up to that point, almost exclusively used just for GPU calculations. A year later, a research group broke all the records for NIST calculations for digits calculations. And a couple of years later, after that, AlexNet, a very famous neural network, was designed and beat all the benchmarks for ImageNet competition by a wide margin. And ImageNet competition has ever since been dominated by deep neural networks. Now, the deep learning and machine learning for neural networks has been growing much faster than Moore's law. This is one of the graphs that shows how much compute you need in order to achieve AlexNet performance by all these latest more efficient neural networks that have been developed. So you see that neural networks are far outpacing the development that we have with Moore's law, which says that roughly number of computational operations per chip can double every couple of years or so. Here, the growth is almost every 3 months. Efficiency of neural net doubles. So we have a situation where Moore's law is becoming increasingly. Moore's law, as defined by the CPUs, is falling increasingly behind best developments in neural networks and machine learning. Here's Moore's laws over the last 5 decades, and you may not notice it quite well, but if you look at development since 2010 or so, we see that there's a little bit of a flattening of the curve over here, and it's very much expected in most of considerations that Moore's law will come to an end within maybe a decade or so, purely because miniaturization that we've been working on over the last 5 decades is coming to the end because of the pure limits of physical nature of the chips. However, we can still go beyond Moore's law if we use parallel computers, and GPUs are most a useful example of that. So why GPUs? So GPUs are started as just a very specific devices for accelerating graphical performance, but they're becoming very powerful and very useful for all sorts of other computationally intensive tasks. Historically, they've been much more limited by the memory size than CPUs, but that's changing very rapidly over the last few years where GPU memory bus has been increasing and becoming faster and faster. So right now, you can have as many GPUs as you want, almost in parallel, working together over the very fast memory bandwidth lanes. So here we go explain what's the philosophy behind the RAPIDS project. So RAPIDS is end-to-end GPU acceleration for data science. The motivation is to bring all of the data science processes onto GPUs and accelerate them to the point they become almost instantaneous for most practical purposes. The scope of the RAPIDS project is actually pretty wide. It's trying to incorporate most of the common data science tools into a single framework, and it's following a lot of most popular data science practices, as well as most of the data science libraries. So this is just a general kind of overview. I'll get back to it in a second. And then one of the main reasons why we can, okay, let me just point this out. One of the main reasons why we can really scale this so fast is because RAPIDS is relying on a single unified GPU memory architecture. Traditionally, most of the applications, most of the libraries have used their own particular libraries and particular way of accessing the memory, but RAPIDS is just working off a single Apache Arrow GPU memory architecture. So if you're a big data practitioner, over the years, there's been a steady increase in efficiency of querying and manipulating big data. Problem, it all started with Hadoop processing, which was very revolutionary for its time, but it quickly came into some bottleneck in terms of performance. Spark improved on that by creating a lot of in-memory operations that improved on Hadoop, and finally moving some of these operations onto GPU. Additionally, improve the processing and the data manipulation that Spark provided us. However, the trade-off was that accelerating parts of the process on GPUs introduced a lot of more code that needed to manipulate and transfer data between CPUs, GPUs, disk, and other units. Now, this is sort of a bird's eye view of how traditionally these GPU-accelerated tasks for data science are done. There's a lot of different places where data is being moved back and forth between the disk and the CPU and GPU, and they're big bottlenecks for like improvement of that process. Now, ideally, we would want to keep all the data on a GPU. So this is where we, inspired by Apache Arrow, RAPIDS project has adopted this as a unified machine learning framework from which we can extrapolate to all the other processes and libraries. So this has additionally improved processing of the data by 50 to 100-fold and really streamlined processing of the big data. Now, RAPIDS core is built atop of the very familiar Python libraries like Pandas, scikit-learn for machine learning and data science, then NetworkX, PyTorch, and Matplotlib for other aspects of the data science workflow. In particular, RAPIDS has created their own version of Pandas and scikit-learn in a form of cuDF and cuML, which try to mimic API for those two libraries. So onboarding and transition to RAPIDS should be fairly straightforward and fairly intuitive if you're already using Pandas and scikit-learn for your daily tasks. So this is a sort of bird's eye view of how a traditional GPU difference between a traditional ETL process and data science process on CPU-powered workflows versus GPU-powered workflows. it really, I have actually been in these situations where, I would come to work, start up my ETL process, wait for a few hours for it to be finished, and then do something else and twiddle my thumbs in between and drink inordinate amount of coffee. So this is a just very quick overview of ETL Technology Stack. It's based on Python and Cython and cuDF libraries. Now, what is cuDF? It's a tabular data exploratory library. It's based on completely on Pandas API, but there are some divergences, mostly because Pandas is very inefficient handling certain kind of data, and there's a overall attempt to converge to a much more streamlined processing. It uses GPUs to speed up common data exploratory tasks, just like data importing, joins, sorts, merges, etc. So it's based on libcudf library, which is a very low-level CUDA library that has a very optimized kernels for joins, group bys, and reductions. But it goes beyond that, and if you import cudf and start using it as Pandas, chances are most of the tasks that you're already familiar with will be directly translatable. So, for instance, you can load the data set, create a nice, in Jupyter Notebook, you can create a very nice presentation of it, or you can do all sorts of joins and sorts that you're already familiar with from Pandas. Now, the biggest, it's one of the more massive improvements compared to other Python libraries for very common data munging operations like merges, sorts, and group bys. It has hundreds of x improvement, when compared on a very particular architecture compared to Pandas. So if you're working with really large data sets, with millions of rows or hundreds of millions of rows, use of cuDF with Pandas with Dask will massively streamline your process, by orders of magnitude. Next one is the one that I'm most familiar with and that I enjoy working with the most, and it's QML. And that's a machine learning modeling library that's built with to make it look almost exactly the same as scikit-learn, with few exceptions. It has all the very familiar sklearn algorithms like logistic regression, k-nearest neighbors, spore vector machines, and random forest. Now, for some of these tasks, improvements are not that dramatic. It would be orders of 10 or 20. But for other tasks, improvements are hundreds of or even thousands of times more efficient than sklearn. And why is this important? One of the main reasons why this is important is now all of a sudden some of the classic machine learning algorithms that have not been used in years, if not longer, are becoming more useful again. And one of my favorite one is support vector machines, which is actually very good, very highly predictive algorithm, but it's been really limited to small data sizes because how slow it is to implement on most data sets. Now with Rapids and QML, that can be accelerated by orders of magnitude. So this is where QML falls within the whole data science pipeline. And again, data sets are only becoming bigger and bigger every day. It's hard and hard to work with them, and acceleration of that you get from having more and more CPUs is not as dramatic as adding bigger and faster GPUs. So you can really do modeling that otherwise would take hours, if not days, be performed in minutes or even seconds. So this is a brief overview of ML technology stack. So here's an example how easy kind of drop in for Pandas and sklearn Rapids is. This is an example of importing data set, one of the standard data sets that's already preloaded with sklearn, and creating Pandas data frame, and then doing a very simple clustering analysis using dbScan. Now, the same code with cuDF and cuML is almost identical without any changes in API. So this is where having a unified API can be very helpful for transitioning from the kind of work and kind of processes that you're familiar with. Now, there's one exception. You probably noticed there's no, we still don't have data sets that you have in sklearn in cuDF, but that's probably one of the features that we'll be working on. Here are some just general algorithms that you have within the sklearn. There are clustering algorithms, regression, almost everything that you have in sklearn, you have in the QML. Now, there are a few, ones that we still don't have, and no, roadmaps for those, like multi-layer perceptrons. But we also have certain ones that do not exist in sklearn. In particular, I would like to alert you to target encoding, which is very useful for machine learning modeling. And here again, benchmarks comparison between QML and scikit-learn. Now, for some of these tasks, improvements are significant but not dramatic. On the other hand, for these that I mentioned earlier, like support vector machines, improvements can be, just staggering. Like 3 or 4 orders of magnitude better than what you'll be doing with sklearn. There are a few other libraries that are a little bit more niche compared to like what most data scientists encounter in their daily work. Like cuGraph is a graph analysis library. If you're working with networks of any kind, you probably need to do some graph analysis. And cuGraph helps you speed up those analyses by, again, orders of magnitude compared to traditional libraries like NetworkX, while maintaining same kind of API. Here again, functionality that you have in cuGraph, which is very similar to NetworkX. And here are some of the Speedup improvements. I would particularly alert you to the last, to these last 2 rows when you have enormous networks. Enormous networks with 16 billion edges and 400 million vertices. You go from 96 minutes down to 31 seconds. So that's a quite dramatic improvement. QSpatial, if you're doing some kind of geographical or spatial analysis, that's a library that helps you visualize data, create geographically based analysis, and present it in a much faster way than you would be able to do with traditional libraries. A friend of mine is working for a shipping company in Singapore, and he was able to reduce some of his shipping lane planning from hours to few minutes using QSpatial. Now, if you're doing signal analysis, there's a QSignal library, which is a GPU-accelerated SciPy signal library, which comes with most of the common tasks that you may be wanting to do with in signal analysis. Now, on top of Rapids library, there are several other projects that are not part of the library itself that people have been working over the last few years. There's NVTabular, which is a very powerful library for recommender systems that's being also developed by people at Rapids. There is, again, dramatic improvement compared to anything that you could do on CPUs. There's a Blazing CQ, which is implementation of CQ on the GPUs. It's built completely on top of QML. Has a very intuitive interface, same as most other SQL database interfaces, and I can bring incredible speedups for most ETL or ML-focused queries that you may run into. So this is part of what we were talking about earlier, data storage and data retrieval. Very intuitive way of getting data from your database into a QDF. Based on what you analyze, you can change your query sequences to actually accelerate this process. Once you're satisfied with the data that you have, pass it on to QML for machine learning, and you can pretty much do a job in a day that otherwise you might have to work on for a week. If you're deploying data science models, then QStreams is another acceleration of processes. It's essentially GPU-accelerated Kafka streaming. Now we're going to come to one of my favorite machine learning tools, and that's the SHAP values. Now, SHAP values come from a game theory where you could explain optimal game theoretic performance based on some sophisticated calculations. A few years ago, they've been applied to machine learning, and there's several implementations of them. Most powerful ones are based on tree-based algorithms, and there's almost actually exact way of calculating them using tree SHAP. One of the things that I like about SHAP values is that they're much more theoretically sound and consistent than other feature importance predictions. However, they're very computationally expensive to calculate, and depending on your data size, can take you hours to calculate for your algorithm their values. Now, GPU, there's currently, and this is like within last week or so, implementation of calculation of Shapley values. There's GPU tree SHAP library, and a new version of XGBoost 1.3, which should be out any day now. There's also a calculation of SHAP values, and these are, I think, the first GPU-accelerated calculations of SHAP values. So SHAP values have a nice property that they're very granular. They have, you can, do feature attribution based on a single row of data. And for instance, in this graph, you can see this is cumulative predictions for each one of the features for a data set that we use for credit scoring. And for each one of the rows, you can pretty much give the SHAP value for it to give you very granular understanding of how your model is performing. Now, aside from interpretation, one of my favorite things about Shapley values is give you contribution on model contribution to the model based on interaction between features. Now, this means that if you have n features, you have n squared contributions that you can calculate. So a computation for these things becomes prohibitively slow and expensive for even moderately large data sets. Now, this is where GPU acceleration of SHAP values really come in handy, because it can accelerate by orders of magnitude, like 500 times or more. One very valuable aspect of these feature interactions is that they can give you idea for future feature engineering, which can help you create features that are based on interaction of 2 or 3 different important features. So this would be sort of one of my favorite applications of Shapley values, but it's still not widely used. So that pretty much concludes my presentation, and I thank you again for your patience and time.